Hello. Last time I actually forgot to hit the recording button, so we'll have to do this again outside of the class. So welcome to the lecture 7 of Deep Learning for NLP. Today we see the decoder-only models and the GPT model. So what we do today is, first of all, we quickly recap the three most common transformer architectures, and we also cover how the decoder block works, because last time we did not. Then we see OpenAI famous GPT model, which is an autoregressive decoder-only transformer, which showed surprising generalization capabilities. And finally, we talked about hallucinations, confabulations, and a bit also about reasoning. So we take a step back, reflect on what this model can and cannot do, and we'll even get a bit philosophical about it. So let's start by the transformer blocks and the language modeling. Okay, so this is just a recap. We saw there are many ways to implement a transformer, so let's see them again very quickly. First, we have the encoder-decoder transformer. So this is a stack of encoder blocks that produces a representation of the input sequence. So example, these models are like T5, BART, Pegasus. And they do this efficiently in the encoder block, because if you recall from lecture 6, we have this parallelization, so we can do the attention calculation in parallel in transformers. Then we have the decoder, which autoregressively produces the output sequence, one token at a time. We cannot parallelize this because the generation must be autoregressive. It depends on the previous context. We'll talk a bit more about it in a bit. But yeah, this architecture is quite powerful. In theory, it's the best of both worlds, because on the one end, you learn powerful representations with the encoder, but on the other end, you also can produce text auto-regressively with the decoder. The problem is that this is quite heavy to train. In a certain way, it's almost like doing 2 times the work, because you need to train both the encoder and the decoder. Of course, these are trained jointly during training, but you might say the effort to converge is doubled. Anyway, it's quite heavy to train. Then we have an encoder-only transformer. So we ditch the decoder block completely. We saw an example of this before, like BERT, but there's also others like Roberta, Electra, Albert, Deberta, and so on. The goal in here is just to learn powerful representations of our words and sentences. We do this in a not only a parallelized way, but also bidirectional, because you remember that like BERT had these characteristics that we see the whole sequence at each step in the encoder. So in a way, this is bidirectional. The problem is that we cannot use it for anything besides the pre-training tasks. Of course, we can circumvent this by using specific elements. For example, we saw in the last lecture that we can add some decoder adds to make BERT do other tasks besides the one he's trained on, which, if you don't remember, it was masked language modeling and next sentence prediction. And then we come to this new model, which is the decoder-only transformer. So this time we ditch the encoder block. And some examples, these are GPT, Llama, Mistral, Falcon, pretty much most of the current models. And the goal is learning how to generate text. So this is very effective in text generation, because autoregressive generation has shown to be experimentally powerful for text. And it also makes sense, right? Also from the human point of view, having to conditionally generate a new word based on what you said before, it can be seen as something which is a proxy of how we as humans generate text. Of course, don't quote me on this. I'm not claiming this is exactly how it works, but I'm just saying it's intuitive. The problem is that we don't have any representation from the encoder, and we cannot use bidirectional encoding. So before moving into more details how this work, we're gonna focus on attention masking a bit. So again, you might remember from the previous lecture that sometimes we want to hide, to mask some tokens if it makes sense for our task. By mask some tokens, I mean that we substitute their score during the attention to minus infinite, or anyway a very, very low value. And when we apply the softmax applied to a vector in which some elements are very, very small, results in the softmax assigning probability 0 to them. So what do I mean? If it makes sense. Well, there are three fundamental masks that we can use. The first one is fully visible, which also means no masking. Basically, every token can attend every token. So this is called an attention mask, but really there's no masking happening. So we use it in general text modeling, for example, for BERT. Now, it's very important that you remember one thing. So uh, you may remember that BERT had some masking, which is dynamic in a way, right? So every token had like some percentage, like 15% chance of being masked, and that masking dependence. 80% of the time it was the mask token, 10% it was a random token, and another 10% it was in a way fake masking. We're not masking it at all. That is not what we're talking about here, right? Because besides that specific task, BERT is still fully visible. At any point, the encoder can see the whole sentence. Then the fact that we alter some of those tokens is another question. In here, we mean actual general masking. So we have causal masking, where every token can attend only the previous one, as you can see in the example. And this is very good for text generation because we're preventing the model from looking at the future, right? Because it will be cheating. If I have to predict the cat is cute, and I am trying to predict cat, seeing like is cute may give me some cues to cheat during training to do some hack to converge very quickly to the solution, but then I won't actually generalize. And then we have causal with prefix, so where every token can attend to the previous one plus a certain amount of tokens, let's say k tokens that we know prefix. It's cool for conditional text generation, so those situations where we have a prefix that is always known and the rest is generated autoregressively. So for example, if I have an extraction there, and as a consequence of this, we have full language modeling. So given the previous tokens, predict the next token for every token in the sequence. We have prefix language modeling, which is we feed a prefix where the mask is not does not have to be causal. And then after the prefix, we start the full language modeling. And finally, we have masked language modeling, which is when we reconstruct max tokens or spans of tokens. And yes, you can see some examples in here. And again, what happens if the prefix contains an instructions? Then we go into all the domain, instruction tuning and having models that do not just autocomplete a text, if you will, but actually learn how to spot instructions in the provided text and do something more advanced. But this will be covered in the next lecture. Now, let's dive a bit deeper into the decoder block. So let's say we learn our very powerful representation in the encoder, okay? So how do we use them to generate new sequences? Where does the decoder block, which is this guy here, come into play? So first of all, we start from the usual beginning of sentence token, which is fed to the decoder with the positional encoding. And after that, we calculate multi-head self-attention with a causal mask, as we've seen before. What it means here is that each decoder block has its own matrix, which uses to derive Q, K, and V and calculate the dot product scale attention. And then we apply the usual residual connection, which is here represented as the usual add and norm. Now, what changes is then that, after we just described these, we now have these. So, what is this? This is called multi-head cross attention, and what changes now is that we want to combine the representation from the last encoder block with the current decoder representation. This is actually very similar to what we saw with RNNs. You remember that we were calculating like attention in an RNN or in an encoder decoder with attention. We used the output of the attention score calculated with each encoder state, and then we combine them in the decoder somehow. You may remember this was done by just concatenation. In the transformer, we don't concatenate, but it's another step of multi-head attention. So the decoder has another set of matrices to again derive query, keys, and value. And via this, we calculate another dot product scaled attention. So it's just the same process and followed by more residual connection. And usually the feed-forward neural network, which, as we saw before, helps us capture more complex relationships and combine the learned information within features of the tokens. So each time we're generating a token, this procedure is applied for a certain amount of decoder blocks. And we then use a linear layer and a softmax to, as usual, map the representation to probabilities over our vocabulary. And that's how we produce a token. Now, you may ask, what happened to parallelization? Because in the BERT lecture, we discussed that the transformer is very efficient because we can parallelize the attention mechanism. But how come that now we go back to sequential processing? Because we said it was very inefficient. And it is, but there are some things that we cannot get rid of. For example, the fact that autoregressive text generation works very well. As I said before, just generating this conditional way is just extremely powerful. It just works. But also, bidirectional processing in parallel is not great for text generation. The model won't learn well. Plus, we are cheating. Again, if I am predicting a sentence, seeing the future during training means that I am cheating, and experimentally doesn't really help the model generalize. Now, you might ask, can we have some kind of hack to use the encoder for text generation? And yes, in fact, we can. So one very obvious hack, for example, feed the model an entire big sequence of mask tokens and ask the model to unmask it. But this basically does not work well because the model is not trained for massive unmasking and the training signal will be basically non-existent. Now, if you think about this, it makes a lot of sense because what I would be asking my model is, let's say I want to generate 200 tokens, okay? It will say, without any context, without any information of what these tokens represent, can you reveal them all? Can you unmask them all? And can you do this correctly, regardless of what they should contain? Of course, it will not work. There is no context. You could not ask a human, for example, okay, these are 200 covered words. What are they? Without any information. And then, okay, now there are 200 different words. What are they, right? So it just cannot work. Now we can move to GPT, the GPT model, learning and prompting. So this is a popular transformer architecture that OpenAI introduced around the same time as BERT. It had 170 million parameters, so slightly larger than BERT base. Yes, right? Yeah, BERT base. And it had 12 decoder blocks with 12 attention hands per layer. So again, big model. It was trained on book corpus, which consisted of 7,000 unpublished books. There's not an official estimate, but so these are not public. Like OpenAI never released the dataset, but it is estimated that it consisted to between 7 and 15 gigs of text. These are the decoder-only model. So again, as we said, no cross-attention mechanism, only the self-attention. And the goal is to predict the next token. So we use a causal mask for language modeling. What about the representation? Because we don't have an encoder. Well, these are learned directly in the decoder. So you can see here that we just attach the representation to the decoder, and that's how we learn them, how we train them. Does it work? Well, we'll see in a bit. But what is important to notice is that if we compare the GPT to BERT, we are relaxing the goal even more because BERT said, I don't need to fine tune, I don't need specific data annotation. I can just model words by unmasking them and model sentences by predicting whether sentence A is before or after sentence B. And then I can learn a powerful representation that I can apply to many tasks, maybe with just a little bit of fine tuning. GPT goes even more on the way of relaxing and say, I can just predict the next token over and over, and I can learn powerful representation that can apply to many tasks. So it actually worked because while BERT was more powerful, the GPT, the difference was very small, like a couple of percentage points. Similar to BERT, GPT proved that we can train a transformer model on a large amount of text, and we can produce representation that can be useful for other downstream tasks. Then it came GPT-2, which, as you can guess from the name, is the second iteration. This time it was a family of model, which went from small, having 124 million parameters. I want to stress here that the smallest GPT-2 model is bigger than GPT-1. And the biggest one, Excel, had 1.5 billion parameters. The fun fact is that OpenAI initially did not open source this model because it was too dangerous, because it was too fluent in producing text, so it would have been used for, I don't know, fake news or something like that. This might remind you of what now is happening with Claude Mythos. So it's not the first time that these companies just goes out of their way and say, yeah, our model is super powerful to the point that it could be dangerous for the humanity. So what changed? I would like to tell you that GPT-2 was like this kind of breakthrough, architecturally speaking, but the point is that it was just bigger. They expanded the vocabulary, they doubled the context length, they trained on a bigger corpus, this web text corpus that consisted of about 40 gigs of text this time, so more than double. And what is interesting, also they apply some modifications like the different layer norm. The tokenization was a bit more robust and a bit more fine-grained, but nothing really crazy. These are things that companies and model vendors do even today. What is interesting is that GPT-2 was the first model showing something called zero-shot learning. In fact, you can see that the title of the original paper says the language models are unsupervised multitask learners. So what does it mean? Well, in general, when we talk about learning, we mean that we are tuning the model parameters, we are changing all the little numbers until the model does something that we want. It produces a desired behavior. So this could be classifying a text, telling us a movie review is positive or negative, or generating a text, summarization, whatever you want. Now, consider a model which is pre-trained on some task, like multi-mask language modeling. And let's consider now a downstream task, which is completely different. We did not explicitly train the model. Now, few-shot learning will imply that we fine-tune the model on a few examples. Few is not really a precise number. It could be 50, 100, 1,000, I don't know, of this new task. And then we use the model to perform it. One-shot learning, it means we fine-tune only on one example of the downstream task, and we trust it will be enough for the model to perform satisfactorily on it. And then we had zero-shot learning, which means we do not fine-tune at all. We just take the pre-trained model, which again was pre-trained on a completely different task, very general one, like mask language modeling, and we use the model to perform it. But this doesn't make sense, right? How can a model solve a task that it never saw? So the intuition is that when we train a transformer, for example, on massive text corpora, this model will basically be exposed to some naturally occurring NLP tasks or some very close proxy of them, so it can learn them. So, for example, you can see here on the right, this is a table from the GPT-2 paper, and it showed that when you open this huge corpora, there is basically, I don't know, the web, just what you find on the internet, you find instances of machine translation. People say, I'm not the cleverest man in the world, but like they say in French, followed by the actual French translation of it. Or if this sounds like a bit of a stretch, consider this question in French, blah, blah, blah. Or did you go to the movies? Which literally translates as, have you go to the movies theater? So while this is not machine translation text, the model sees instances of parallel translation, right? English and French, French and English, and so on. So when we prompt the model to perform a task, it may recall seeing these examples during the training and actually be able to do it. So this actually happens. In the GPT paper, they say we test if GPT-2 learned how to translate. So to help it infer that this is the desired task, we condition it on a context example of pairs, for example, an English sentence and a French sentence, and then we sample with grid decoding and use the first generated sentence as a translation. The result is that GPT-2 was just slightly worse than an unsupervised baseline, which is not great. It's not like it was state of the art, but it still showed you that a model trained on completely different stuff, like just predicting the next word, also lets you learn other tasks. Not only, GPT-2 could also do some zero-shot question answering. So you can see here, again, from the GPT-2 paper, some questions that were asked to the GPT, right? Who wrote the book of the origin of the species? Who is the founder of the Ubuntu project? Or who came up with the theory of relativity? And GPT-2 can produce very, very often correct answers, has the most probable tokens. For example, it will answer Charles Darwin for the who wrote the book of Origin of the Species, or will answer Albert Einstein for who came up with the theory of the relativity. Why is this happening? Is because probably while predicting tokens on huge amount of text, GPT actually saw text in which like the tokens Charles Darwin appeared very close to the origin of the species. So it inferred with a bit of generalization that these two things were related. And causal language modeling can take you very, very far. So consider Olmo. Olmo is a decoder-only transformer from Allen AI. If you don't know Allen AI, look into their job. They're super cool. They release everything, including the full pre-training data and the code. So given that you have enough GPU, you can basically retrain Olmo from scratch and obtain the same model. So I'm going to ask you a weird question. Was Olmo trained to write the introduction of The Lord of the Rings or the introduction of books in general? Well, you could say probably not. But let's say yes, because maybe The Lord of the Rings is a very big book. It was interesting. Alan AI wanted to put it somehow. Let's assume this. Now, let me ask you another even weirder question. Was Olmo trained to write short bios about people, for example, about me? Well, most probably not. It's even weirder, right? But if Olmo read some stuff about Lord of the Rings and Dr. Simone Ballocco, for example, during pre-training, because maybe my name is on the internet, and there is a lot of text about Lord of the Rings of the internet. Can it somehow infer from a prompt what is possible to write if I ask him to do these tasks? Well, this is a rhetorical question because, of course, it can. So in here, I ask Olmo to write the introduction of the Lord of the Rings. Now, ignore there is a part of Italian because probably they geolocalize me and try to try to answer to me in Italian, even if I ask in English. But you can see that first of all, well, I'm stupid because it says there is not a section called introduction in the Lord of the Rings, which I forgot. They say what you're maybe referring to is the first part, the first sentences. And then he says, in a hole in the ground there lived an hobbit, not a nasty, dirty, wet hole filled with the ends of worms, blah, 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 blah. And what is cool is that Olmo gives you this Olmo trace tool, which basically searches the whole training corpora and tells you, oh, this sentence actually comes from this web corpus. And yeah, you can see that these exact words are there. Oh, and this other is there. So again, causal language modeling can take you very, very far. Now let's go to the example about me, right? So if I say, write a short paragraph about Dr. Simone Ballocco, who is teaching deep learning for NLP at Darmstadt, it actually makes sense. It does stuff like Simone Ballocco is a researcher, blah, blah, machine learning, deep learning for NLP is a study of deep learning applications, theoretical foundation, blah, 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 blah. Now, if we click on Olmo Trace, you see that the text for which he found Simone Ballocco is not related to this course at all. It's actually a blog post by my ex-PhD supervisor, which talk about my research. Still, it talks about NLP. But you can also see that this sentence, a comprehensive study, does not come at all from deep learning for NLP or AI in general. It comes from an article about an art exposition of expressionism in Darmstadt. But by combining this information with the fact that I asked him to talk about someone who is teaching deep learning for NLP, he was able to make something that makes sense. Now, does it also work if I give it less hints? Actually not, because I try to just ask Olmo to write a paragraph about Dr. Simone Ballocco without any other information, and actually started saying that I was working for Allen AI, which is definitely not true. So the causal language modeling can take you far, but only so far. Now we can move to GPT-3, and this is quite an interesting thing. So it's the first model that OpenAI never open sourced. So GPT was never released. It could only be called by API calls. It was, again, a family of model, but the most notorious one had 175 billion parameters, so we're moving several scales up. It had 96 layers with 96 attention heads for each layer. Again, we doubled the context length to 2048 tokens. And these were trained on a lot of data, like a filter common crawl, which is basically the internet scraped. WebText2, Books1, a lot of stuff, English Wikipedia. These amount accounted for almost half a terabyte of text. And GPT-3 shows surprising performance from what we now refer to in context learning. Now, what in context learning is the phenomena by which a language model learns how to solve a task at inference time without any change to its weight, based only on examples in the input, which is now called a prompt. So from the GPT-3 paper, they say that during a supervised pre-training, a language model develops a broad set of skills and patterns, patterns recognition abilities, then uses these abilities at inference to rapidly adapt to a specific task. We use the term in context learn to describe the inner loop of this process, which occurs within the forward pass, so no parameter changing. Now, the term in context learning is confusing. Everything is becoming very messy because learning refers traditionally to when we change the model weights during training. In this case, that's not what happened. So that's why we call it prompting. And we have various flavors of this. We have zero-shot prompting, which means that I give you a piece of text in the input, and the model has to predict just by the natural language of the description. The natural language description of the task. So, for example, if I ask the model translate English to French in a given cheese, then I will hope to obtain fromage. Few-shot prompting is the same thing, but we give also some examples. So, for example, translate English to French, and we give them sea otter, which is translated to loutre de mer, and we then give the cheese and hope to obtain fromage again. Then we have few-shot prompting. This time we have few examples. It can be 1, 2, 3, 5, how many you want, right? And hopefully it works even better. So does prompting work? Well, yes, GPT-3 without any fine-tuning showed to be able to perform better than the supervised alternatives, and sometimes even better than supervised state-of-the-art, all without being explicitly trained on these tasks, but just by, again, causal language modeling. I can also show you an early example of one-shot QA in GPT-2. So you have this huge text passage we will not learn. Basically, you have your prompt, your demonstration. This is the one-shot. So, for example, how old is Catherine? And the answer is 54. And if you look in the text, you might actually see that Catherine is indeed a 54 years old secretary. Then we have the whole prompt. And the answer of the model to the second question, which is where does Catherine live, is Stockholm. While the Turker's answer, like the human annotator's answer, will die Sweden or in Sweden. In fact, you may notice that this is wrong. If you read this whole text, which we're not going to do now, is never specified in which city Catherine lives. They only say that she lives in Sweden. So why is the model wrong? Why is our model not perfect despite all this crazy improvement in causal language modeling? Well, this takes us to the very, very trendy topic of hallucinations, or how people call it confabulation, or, some people, there are a lot of terms for this phenomena. But what is happening is that while causal language modeling can give you surprising generalization, it's still predicting the most probable token to complete a sequence. So the most probable doesn't mean the correct all the time. So what happens if at some point we predict the token XY and this token is wrong? Well, what will happen is that the model will autoregressively condition on it. So we will predict the token XY plus 1 based on a wrong previous token. And if this new token is wrong again, we're going to propagate the error more and more. And this causes the known problem of hallucinations or confabulation. So initially, when we had models like GPT-2, these were very malformed nonsensical text or endless repetition, like the text was basically broken. With GPT-3 and even today with ChatGPT, Claude, blah, 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 hallucinations are kind of harder to spot because the text make a lot of sense on the surface, but it cannot be checked, right? You cannot tell if what is being told by the model, what is being generated by the model is actually true. Or if you can check it, it's wrong. Also note there is an ongoing discussion on whether hallucination is a good term. Some people calling for confabulation, unfaithfulness, lack of fidelity. We don't care about this, right? So this is just for general information that the problem exists. Now, these are some examples. As I said, GPT-2 hallucinations were pretty bad. So consider this. The input was, if you have severe breathing problems, you should get help immediately. The output say, you may not need hospitalization for respiratory problems for which there is pain or even full internal combustion, which is already weird. It continues to say, breathing is particularly hard in the high pitch, low pitch pitches, which doesn't make sense at all. Air you inhale and exhale can cause a shortening your breathing, so a ventilator is best. Doping can be administered on your own, and so on. The text just completely, takes the tangent and goes completely bonkers. In GPT-3, we have other other different hallucinations. So, for example, stuttering. For the input sentence, a man in a chef hat prepping some food, we obtain a man is sitting in a IAA. Or we have a sentence fragment where, we have, for example, a large brown horse eating a globe of leaves results in the model generating a horse eating a piece of tall brown. So just kind of copy pasting parts of sentences. And then you have the actual hallucination. So consider the sentence, two tables next to each other along with laptops. The model generates two people sitting on the beach with their laptops, but there's no mention to people in the input sentence. It is plausible that there could be people sitting at this table, especially if there are laptops, but it's not actually, we cannot say it's true. A city street line with very tall buildings results in the model saying a city streets with several signs of the street. Now, while it's how do you say, probable that there are several signs on the street, this is not said in the original sentence. And even today, we did not get rid of hallucinations. So what I have here is an example from Dr. Yejin Choi talk. Dr. Yejin Choi works on common sense reasoning, which is a very, very cool topic, basically trying to entrust that our models build a solid word representation in terms of societal values, culture, and so on. So I'll just leave you to it.
AI is passing the bar exam. Does that mean that AI is robust at common sense? You might assume so, but you never know. So suppose I left 5 clothes to dry out in the sun, and it took them 5 hours to dry completely. How long would it take to dry 30 clothes? GPT-4, the newest, greatest AI system, says 30 hours. Not good. A different one. I have 12-liter jug and 6-liter jug, and I want to measure 6 liters. How do I do it? Just use the 6-liter jug, right? GPT-4 spits out some very elaborate nonsense.
Okay, so this is just to say that there's been an ongoing narrative saying that, hallucination will be fixed. We just need more data. And that has been said for GPT-2, GPT-3, GPT-4, GPT-5, Claude. And, if you really understand the mechanism of autoregressive generation, you understand that probability cannot be disentangled by the fact that you will occasionally produce something wrong. Related to this, we can also talk about reasoning. So zero-shot and in-context learning basically bent the laws of what we thought it was possible to do with language modeling, right? Just predicting the next token. Now these models can do a lot of stuff. Some researchers go as far as to believe that this model might be proxies of human comprehension of language. Sometimes they even say, these models are reasoning like a human. They're becoming sentient in a way. If you go ask to OpenAI or Anthropic, they will even tell you this is like something called AGI, superhuman intelligence, anything that will basically keep the investors happy. Now, it is true that if you prompt your favorite LLM today, you often get an almost perfect answer, and the mistakes are easily fixable. You need some basic understanding of the topic. But can we assume that this means that LLMs move beyond statistical token modeling? Also, you may say, okay, I understand the argument, but I yesterday asked my LLM something extremely specific, which cannot be on a web corpora. And by this, I invite you to refer to The Illusion of Uniqueness by Schneider and Sneckel, a very, very cool, very old psychology paper, which shows you that, your queries are not so special. You may be surprised to understand what is on the internet. But I'm going to show you this by an actual example. So consider the Schrodinger's cat problem. And the Schrodinger's cat problem, if you don't know, is this problem where you have a cat which is in a still chamber, and the cat is together with a diabolical device, a Geiger counter, where basically there is some radioactive substance. In an hour, the atom could decay and cause the cat to die, or it could not. Basically, there's equal probability. So if you leave this system closed, like the cat in the box with this device for an hour, what are the chances that the cat is alive or dead? Now, this is a very well-known problem that relates to the superposition of states and quantum probability. And needless to say, this model, which is OpenAI o3 from last year, nails it. It tells me, yeah, it's the Schrodinger's cat, illustrates quantum superposition, blah, 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 50-50 probability, and so on. Okay, so we can assume that ChatGPT knows this problem well. Now, is it safe to assume that ChatGPT actually understood the underlying problem? So let's make a little modification and say now there is a dead cat in a still chamber with the same device. So after an hour, what are the chances of the cat being alive or dead? And of course, now they are zero. And yet, ChatGPT still says that there is 50-50. This is still the Schrodinger cat problem. Why? Well, probably because this is 99.9% the same text with just a little modification. And in fact, you can even notice that in the reasoning trace, ChatGPT says, oh, they mention a dead cat, which might be an intentional twist, and then still ignores it. Now, can we fix this? Yeah, of course. If I now say a dead cat who is dead and cannot be alive is in the still chamber, then now ChatGPT understands, oh, okay, now it's 0% probability of the cat being alive. So not ideal. So this was just for a bit of food for thought. Don't always believe what the company tells you. And autoregressive text modeling is still autoregressive text modeling. That will be the end, and I'll see you, well, in the next lecture.